Greetings, everyone. Welcome back to calculus. It's time for us to expand the usefulness of our derivative even more by talking about higher order derivatives. All the idea here is being able to take the derivative of a derivative. So think back for a second to what we defined the derivative to be. We had several different ways of looking at it, right? We said slope of a tangent line, but we also said instantaneous rate of change. Okay, let's focus on that word rate and then think about what would it mean if I were to take the rate of change of a rate of change, right? So basically the derivative measures how fast something is changing and whether it is increasing or decreasing, right? Because if the derivative is positive, that means I'm gaining, right? Because it's a rate that's adding. Whereas if the derivative is negative, then the measured quantity is decreasing because it's subtracting, right? So back to the original question, what would it mean if I took a rate of change of a rate of change, right? I would be measuring how quickly my rate of change is changing. So the nearest thing that makes sense to something that you do every day is acceleration, okay? Speed is how quickly your position is changing. So speed is a type of derivative. So then acceleration is how quickly is my speed changing, right? That's why that pedal down there is called the accelerator. So the acceleration would be a derivative of a derivative. In the real world application. Okay, so let's start defining these things. We've already talked about the first derivative is what it's actually called. We called it the derivative function, right? The first derivative is when you actually take a derivative of a function. This is measuring your speed, your rate of change, right? But it can also be slope of a line tangent to the function, okay? Then you can have the second derivative. It's symbolized with squares in certain locations of the rate. Notice the square is on the d here and on the x here. When technically the squared is on the dx at the bottom there. It's on the whole thing. Okay? And this is the reason why it's symbolized that way, because the derivative symbol can be thought of as the d over dx. Okay? So if I were doing that twice, d over dx once, right, is here, and then d over dx twice would be two derivatives. Okay, one derivative has a single tick mark, a prime we call it. So a second derivative would be a double prime. Okay? The third derivative, you can keep going with these things, right? The third derivative has a similar format because you can think of it as taking the derivative 3 times from your original function, and it could be f triple prime. But after that point, and maybe even at that point sometimes, we quit writing so many tick mark primes because they just start getting jumbled together and it doesn't make much sense anymore because you just have mark, and it just be senseless, right? So what they start doing is they start putting a little number at the top right here, and you have to remember that's not an exponent because f is not actually a quantity. F is a function, and when we put the little 3 up top there, we mean that it's the third derivative of the function f. Okay? So, a little sidebar here. Calculus, one of the main reasons it was invented, one of its 2 main inventors, Sir Isaac Newton, thought it up for applications in physics. Okay? A big misnomer, though, is the fact that velocity is always the first derivative and acceleration is always the second derivative. And I want to clear this up a little bit. You have to have a function that's based on time before you can say that your derivative is velocity or speed and the second derivative is acceleration. Okay? Because over here, I'm doing derivatives based on x, and typically x is a length measurement. Typically. It doesn't have to be. This is sort of a generic also. X can just be whatever your axis is over here. However, whenever we have a function of little t, a lot of times that means time. And if you think about this, this makes sense. My rate of change over time isn't the speed of what I'm traveling. Okay? In physics, they actually, very clearly distinguish this. Your position x or a position y, sometimes you can have a little bit of both, and you can move around a two-dimensional plane. Okay? These two quantities are distances, they're positions, and they're each some function of time. Okay? So my first derivative, df dt, okay, I could also write dx dt here, since it's x, is f prime of t, the first derivative. But you see how t is the independent variable here? That means df dt is f prime of t. In physics, they also use a little dot over the measured quantity to represent a derivative with respect to time. They still have the prime if it's in the function notation, and that could also be a derivative with respect to x or anything else. Okay? But if it's specifically time and you just have the measured quantity, like x, then the single dot over it like that means one derivative of time. So what do you think two dots means over it, right? That would be two time derivatives, right? So that's the acceleration. The second derivative with respect to time. How fast is your speed changing is your acceleration. So that's a second derivative. Now in physics, they take it pretty far, depending on the application, right? They also have a name for the third, fourth, fifth, and sixth derivatives, okay? The jerk is the third derivative, because if you think about your acceleration measures how quickly your speed changes, your velocity changes, right? Then what measures how quickly the acceleration is? Like, what's the difference between pushing the pedal a little bit on your accelerator or slamming it on your accelerator, right? Pushing it a little bit on your accelerator is, right? While slamming it's like, you get a huge jerk. Hence the name, right? Your acceleration rate of change, how quickly is your acceleration changing, is called your jerk. How much are you getting jerked around, right? Not the mean kind of you're a jerk. No, not that kind. Sounds funny though, doesn't it? And then, of course, because physicists like to be cute, the fourth, fifth, and sixth derivatives are called snap, crackle, and pop. Because those are cute serial names, of course, but they're also indicative names that give you the feeling of being, thrown around. The way your jerk changes is your snap, right? And then, of course, they continue with the name. So the physics applications of derivatives, especially in your first physics course, come in very much with time derivatives and measuring position, velocity, and acceleration. Of course, they use other derivatives in physics to measure any sort of change. That's sort of the basis of all of our sciences. You can't do anything unless you can measure a change, hence derivative, right? But these are the first times that you'll see derivatives in physics. Next, let's take a look at some relationships between taking a first, second, possibly a third derivative, and how the graphs look. Okay. So let's use our ideas of derivative to talk about relationships between the graphs of a function and its derivative and its second derivative. Okay, because this is going to come up sometimes. You may only have a graph, and you may actually have to identify or draw for yourself something that has the relationship of being a main function and its derivative, and just locate the points between the two graphs that line up for that. Okay, so let's start on the algebra side, and then we'll talk about the graphical side, right? Let's take a couple of derivatives here, and then let's graph them over there and look at the lineup. So here's my original function, right? F of x equals x cubed minus 4x, and it has x-intercepts, zeros, at -2, 0, and 2, right? Because if I set this equal to 0 and solve, those are the solutions I get. those are the places that it hits the x-axis, right? Okay, so first derivative, remember, is the limit as h goes to 0 of x plus h cubed minus 4x plus h minus x cubed minus 4x all over h, right? And remember, we can cube this out, right? And then distribute the negative 4 and then distribute the negative here. So I have limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus 4x minus 4h, and then minus x cubed plus 4x all over h. And you can start doing your reductions, right? So plus x cubed minus x cubed plus 4x minus 4x. Everything else has an h in it, so I can start reducing, right? H over h is 1. H over h, here leaves 1 behind. Here I'll have 2 left behind. Here h over h is 1. So what am I left with? I have 3x squared, 3xh. I have h squared and negative 4, right? Take the limit as h goes to 0. So my first derivative function is 3x squared. H goes to 0, so this goes to 0. Same thing here, this goes to 0. Minus 4. Okay, so there's my first derivative function. How then would I find my second derivative function? Okay, so my second derivative would just be, again, the limit as h goes to 0 of 3x plus h squared minus 4 minus 3x squared minus 4 over h. Okay, so again, I would FOIL this out. I would distribute the 3 and take the subtractions, and the limit as h goes to 0. You would find that what you would end up with from in here is a 6xh term, and the h's would reduce, so I'm left with a 6x. Minus 4 and plus 4 add out here, so the 4 doesn't even add to the calculation here. So my second derivative is just 6x. Okay? The third derivative, by the way, would just come out to be 6. And you can tell that right away because you can see this is linear. And remember, the slope of a line doesn't change. So 6x, his slope is 6 everywhere. So I know my third derivative is going to be 6. Or you could go through the bother of the calculation, right? Okay, so here's my first derivative. Let's start with putting the first derivative over here, right? What are the zeros, in other words, the x-intercepts of this function? If I set it equal to 0, I would have to add the 4 and divide by 3 and then square root. So I would get x is plus or minus square root of 4 over 3, which is right around plus or minus 1.15-ish. Okay? Let's go ahead and do that for the second derivative also here. You can see it only has a single 0 at x equals 0, right? Okay. That's just to help us graph this a little bit here. So the first derivative, you can see what it is. It's an x squared, right? That's a parabola facing upwards, right? 3 just makes it a little skinnier, and then it's shifted down 4. Okay? So what I'll need to do is extend this a little bit. Right? Put my negative 4 on there. Like so. and it would have to go through this point right here, right? This would be his intercept that was shifted down 4. And then his intercepts are right around 1.15-ish. So right here, and right here. And we have this. This will be f prime. Now what I want you to notice here is the relationship between the derivative and the original graph, okay? So the key first thing to notice, where these intercepts are here and what that means on the graph over here, right? Those are sort of like separators here. Notice the first derivative goes through the x-axis at the same places where the original function is either at a maximum or a minimum locally, right? Not a coincidence, okay? Let's go from the tangent line standpoint. The red graph here is representing the values of the slope, okay? So if you actually draw the tangent line at that peak, it would have to be horizontal, which has a slope of 0, right? It's not increasing or decreasing there. So I have a 0 derivative, right? Again, same thing here. Next, notice the original function here, if you're reading it correctly, is increasing. That means at each of these locations, my slope would have to be positive. And you'll notice on that interval, the first derivative is completely above the x-axis, right? This is a region where the first derivative is positive. Okay, so that makes sense also. All my slopes are increasing, so my first derivative is positive. On this region from here to here, it's completely decreasing. Notice my first derivative is completely negative from here to here. It's all negative y values, and my function is decreasing. Okay? And then lastly, again, from here on out, it's increasing again. My slopes are positive, and my first derivative is completely above the x-axis, which are positive values. Okay? So then what about the second derivative? 6x, right? Well, that's just a line that at 1/2 goes through 3 like this, goes through the origin, and at 1/2 goes through like this. So I'd have a graph something like this, pretty steep. Ish. Like that, right? Okay. This will be f double prime right here, right? So again, the relationship to its derivative. Okay, so that would be the relationship of the red graph to the blue graph. Notice the red graph is decreasing until this point in the center, right? And the blue graph is negative below the axis until that x value. And then the red graph increases, and his derivative is completely above the x-axis there, so he's positive. Okay? So what you need to be able to do is to look at a graph and the graph of its derivative and see the relationships between them, right? Whenever the derivative graph is above the x-axis, the original graph that it is measuring should be increasing, and vice versa. If your derivative graph is below the x-axis, then your original graph that it's measuring should be decreasing. And everywhere your derivative graph goes through the axis, you should have some sort of, well, we call them critical points, but for now, max, mins, those sorts of things when you're looking at these graphs, okay? Let's get a couple of more examples of drawing graphs, but before that, take a look at these things in Geogebra so that you can see more precisely what I'm talking about. All right, guys, before we move on to the next scene, let's take a quick look at what we just drew on the board. Geogebra will allow us to see it in a lot more detail. So I'm going to type in the function y equals x cubed minus 4x. And there's that same graph that I had drawn for you. As you can see, it already assigned the letter f. And let's also start with the derivative. Y equals derivative of f. And there it is in gray. Let's put it in a brighter color so we can see it a little bit better there. Very good. All right, let's zoom in a bit. And to make it a little bit easier, we'll stretch out the x-axis here. So that's really what we're interested in anyway, is the x-axis. Okay, so I want you to just notice some of the details here. You can see in the green right here is our original function. It is increasing up into this peak point right here. Okay, and that peak point is exactly the same point that this thing hits 0, and that's not a coincidence, right? The derivative is 0 at this maximum point here, and therefore our derivative function is 0. Same thing for this minimum point here, right? It's hitting the 0 marker right here, right when this thing is a minimum there. Okay? And then let's do the derivative yet one more time. Let's see. Derivative of g. And I believe we drew that one in blue, so let's go ahead and make him in blue. We can. Yeah, we'll just force it. There we go. So then here, I know it says g prime because g didn't have a prime on it, but technically what we've done now are two derivatives. And if you just focus on the red graph here, you'll notice it is decreasing up into this center point here, which you'll notice the derivative is negative up into that point. And then it is increasing, and the derivative is, of course, positive. Okay? To finish up this short little Bridger lecture here that I have, I just want to go through a couple of graphs and do some higher order derivatives graphing, right? Like we were just sort of doing in the last scene, but now from the other direction. Now instead of seeing an equation, let's try and look at a graph and draw an approximation of what we think the derivative graph would look like, right? So here we go. I have some function of x. The y-axis here is not important because it's all about the way that it's changing from point to point, right? Okay, so let's go from left to right and see what's going on, right? Okay, so look, right here, I've got something that looks like it's having some sort of horizontal asymptote, right? It looks like it's having some sort of horizontal asymptote, and to be honest with you, whether the horizontal asymptote was way up here or way down here, it really wouldn't matter. The idea of the horizontal asymptote is that it eventually wants to flatten out. Now, of course, it wouldn't totally flatten out until it reached the negative infinity spot, but it's trying to, right? So from the left coming this way, it's increasing, right? And you can see it's going up this way, right? So remember what happens when something's increasing. Which way is the slope going to be of the tangent line, right? So imagine some little tangent lines or draw them yourself. You can see that all of these lines would have positive slopes, right? And it's increasing. So in this region, up to this point right here, my derivative should be positive, should be above the x-axis, right? Okay, I'm going to draw it in just a second, though. I need a couple of points of reference. The next one is this. What kind of point was that again? Oh yeah, cusp, right? Sharp and pointy. Remember, we can't take the derivative at those points. The derivative doesn't exist at sharp cusps like that, okay? In fact, this one's going to be an infinite one. Look, it's going to where it's straight up, and then the other side is also straight up like this. Those are going to end up being a vertical tangent type of situation. So here's what I'm going to do. I am going to draw an asymptote there, because the derivative is going to be undefined at this one point. So I'm going to draw an asymptote here. This is not an asymptote for the original function. It'll be an asymptote for our derivative. And I'll go ahead and string it down here too. Okay? Like that. Good. So the asymptote there is to help me see that the shape of my derivative is going to try to be infinite. It's going to try and hit this vertical asymptote, because the thing right here technically is trying to do a vertical tangent, but it's trying to do it two different ways, and it's making this cusp. Okay? Notice it's increasing, then it's decreasing. Okay? But right now we're coming from left to right. So on the increasing side, then my derivative is going to do this. Like this. Okay? The horizontal asymptote here is telling me that I need to try and approach zero, because it's trying to flatten out. But at the same time, whenever it comes towards this cusp, the derivative needs to become infinite, right? And it's increasing, so it needs to all be positive. So look, everything here is above the x-axis, right? Now, on the other side, it's decreasing up until this point right here. This point right here is a minimum, a local minimum. So this point right here has a spot where the slope is zero, and it's actually changing from decreasing into increasing, right? So this needs to be a spot right here where the derivative is going to change from negative to positive. In other words, it's going to go through zero, right? Okay, it's decreasing this whole way. That means that even though it's coming up to this cusp, right, which makes it an infinite, a vertical tangent, but it's negative because it's decreasing in this direction. So it's going to have to come from the negative infinity. And it's going to have to slow down a little bit, right? It's going to keep slowing down until it gets to this point. So it's going to come up like this. Now, is it exactly like that? No, not exactly, but I'm sure it's pretty close, right? It's going to approach this point. It might be a little bit more straight line there. It might be a little less. Remember, this is just us approximating about what it should be. It's in the correct region, and it's infinite or negative infinite where it needs to be, and it's zero where it needs to be. Okay? Now, let's take a look at the slope in this section. It's increasing. Don't let it fool you that this part of the original function is negative. We don't care. What we care about is it decreasing, is it increasing? Okay? Is the slope of my tangent line positive, or is the slope of my tangent line negative? Okay? And from this point on out, it's positive. So from after this point, all of my derivative needs to be positive, needs to be up here. Right? And it looks like it's getting steeper as it goes. So I'll come up here like this. Right? And possibly, let's see. Yeah, let's see, it's gonna start curving up this way, right? It looks like it's curving here. So that means it's getting faster and faster here. So right about here, it's going to change and go upward also for this guy. give or take. I mean, this thing could actually be a lot wider out, because this thing's a little slow. If we wanted to be a little bit more precise, I guess we could do that. Let's try that. Probably could be a little bit less steep there. Maybe something like that. Sure. Okay. So we'll put some arrows on these things here. Right? And that's F prime in red. So then how would I go about F double prime, right? Or again, this is going to be an approximation off of an approximation, so it'll get a little worse. But we can basically look here what we have and then just sort of try to fix the same way, right? I'm looking at the red graph now, and I'm determining where is it increasing, where is it decreasing, that sort of thing, right? Okay, so from here to here, it looks like it's increasing, and it gets really, really steep. In fact, it becomes undefined. I want you to notice that if the first derivative is undefined, every derivative after that is going to be undefined at the same location, right? It's undefined here at this vertical asymptote. The second derivative is going to have no choice but to be very, very similar here. The second derivative is going to do the same thing. It's going to be undefined at that same vertical asymptote. However, this part of the first derivative is increasing, isn't it? Right? So that means on the other side right here, I'm coming from the positive infinity. So it volcanoes on this thing like this. Now, why am I decreasing here? Right? Well, look at it. The slope is getting a little shallow, right? It's still increasing, okay? And it never totally flattens out, and then it starts increasing again, right? So it gets really low here for a little while, and then starts to pick back up again, right? So I got my second derivative there. Approximation, right? But you get the idea. You sort of got to see what's going on, right? And you're looking for trends of, is it going up, is it going down, okay? And later on, after we've done a lot more with derivatives, we'll even have a more precisely defined relationship between these three levels, especially the original, the first derivative, the second derivative, okay? There is an actual relationship between second derivative and the original that we'll study in depth. And eventually this will help us with what we call curve sketching. All right, let's do one more. Let's say I have this position function, I'll call it P, of time, right? So let's say this is a physics application, right? I have some particle that's oscillating in some sort of electric or magnetic field, right? Let's say the particle's doing this, right? What kind of function is that? Do I need to give you a sign? Right? It goes through 0, 0, right? It looks a lot like a sine function. Now, is it actually? I don't know. We didn't draw the rest of it, but if it was sine, right, should keep going forever and ever. Let's draw the first derivative, right? This is P of t. Look for some indicating spots. First, right here, look. This is a peak, right? The tangent line is going to be horizontal there with a slope of 0, and it's switching from increasing to decreasing. So I know that my derivative should be hitting 0 there, right? Okay. Next, here's this spot right here where it's doing that same thing again, right? The tangent is horizontal here, and then one more right here. Okay. Also, I can see that my greatest amount of increase, look at the slope right here, right? It's sort of shallower here, and then it turns, right, like this, and it gets steep, but then after this point in the middle, it starts to turn back towards being flat again, right? So right here in the middle is like a maximum, if you will, right? Like there's some sort of maximum point, And then right here, in between these two, it's decreasing, right? But it's kind of not very decreasing yet, not very negative slope. And then it gets to be a pretty steep slope, negative. And then it gets back, it turns back in the other direction, being flat again, right? So at this point right here, I would say that this is the most negative that the slope is going to get right here. So you might even say, it's somewhere, how far did I get there? Yeah, about like that. Let's draw what we have so far with this thing. Like that, right? Right? You can see that right here at this point, it's all negative from here to here. And the function here is all decreasing from here to here, right? But it slows down, which is why it's less and less negative until it hits 0. Then it increases from here to here, which means it's all positive from here to here. But it speeds up to a maximum and then slows back down again, right? This kind of thing you should expect if something is oscillating in a field, if something is going back and forth with some sort of field that's keeping it trapped, or maybe it's some sort of square well that's keeping some particle trapped between two fields maybe, or whatever, right? That's what you should expect. If it's moving in one direction, but it's got to turn around, right? That means something has to slow it down and then speed it back up the other way, and then slow it down and then speed it back up, right? So you should expect the velocity to be doing this, right? This would be P prime right here. Right here, at this point right here, where it goes through, is the another highest negative point again. What graph does that look like? If the one in black right here looks like sine, this one starting at a peak looks a lot like cosine, right? Yeah, you should expect that. The derivative of sine does lead to cosine, okay? We'll actually go through a proof of that in the next few sections. This would be P prime, or P dot, one might say, right? Because I'm doing a derivative with respect to time. Let's write that a little bit better. This would be P dot of t, where this one here is just P of t, right? And of course, I could also put dp dt, just like over here, I could have put df dx, right? And so on and so on. But we said that this was the physics application, so I'll use their terminology, right? The dot insinuates a time derivative. All right, let's do a second time derivative. This is the velocity, right? This is the position, the velocity. So the second time derivative would be the acceleration. Let's look at the acceleration. This thing's at a peak here, right? And then it starts to decrease to a negative, right? So that means right here it would be 0. The second derivative would start at 0 because it's peaked out there, right? It's turning, but it's going negative. And it decreases from here to here. So I would expect something like this. Because again, it's the highest negative here in the middle, and then it slows down and then speeds back up again, but increasing. So I would expect here at this peak, right, it would go through the axis again, and it would do something like this, right? You should be seeing a pattern here. Here's that minimum right here. So about right here. Like that. This would be P double dot, the acceleration, right? And again, that should look like another function, right? Negative sine, because it is starting at the origin, but it's going down this time, okay? You just need to see the patterns in the changing, right? The original function here, written in black, is increasing, so its derivative is positive. Okay, next level down, the derivative function, the red, is decreasing from here to here. So his derivative is negative from there to there. Okay? So we have these relationships from one function to its own measured derivative that's based off of position, right? Where I am at this position, now I am decreasing to this position, and so on and so on. Okay? So I hope this has helped you understand a little bit more the relationship between a function and its derivative function, and also that you now realize that we have several derivatives that we can take. Stay tuned. The next several sections we'll talk about how to more easily find derivative equations.